Paula, and hello, everybody. Sorry, there's a cold going around at the moment. So a quick introduction. I'm Frances, and together with Matthew Hort, we've put together this presentation today. I lead the science team at the Met Office, who are developing the quantitative volcanic ash forecast for the London VAC. Matthew is the Principal Fellow in Hazard Decision Making at the Met Office. Our aim is to introduce you to the new quantitative volcanic ash forecasts and to show you how they are useful when considering the hazard to a volcanic ash cloud. Back in the mid-1990s, a network of 9 volcanic ash advisory centres was established, or VACs, and their areas of responsibility cover the world's airspace. And their role is to provide advice and guidance to the aviation industry to aid their decisions as to whether it is safe to fly. This advice comes in the form of a forecast, and these are generated using sophisticated systems, making use of both models and observations. Because we are generating a prediction for the future, all of the VACs use something called an atmospheric dispersion model. These are initialized using information about the release of ash into the atmosphere. So we want to know which volcanoes are erupting, where is ash being released, at what height is ash being released into the atmosphere, and how much ash is being released. And collectively, we call these the eruption source parameters. Our models are also driven by meteorological data. We want to know, quite simply, which way is the wind blowing. So we need to know what the weather forecast is. And both the weather forecast and the eruption source parameters are underpinned by observations. So we then run our dispersion model and we generate a lot of model output. And again, at that step, we compare model output from now and in the past to observations, namely satellite imagery and retrievals, but we can make use of a lot of different observations, including pilot reports. Often our VACs have something called data fusion too, which enables us to better match our model output from the past to observations, which helps to provide a better prediction for the future. And once we've done all of that, we then generate the final product for our customers. So traditionally, this has come in the form of a volcanic ash graphic, or VAG. And we have an example of one of these on the left-hand side of the slide here. And these indicate the expected location of the ash cloud, defined as concentrations greater than 0.2 milligrams per meter cubed, up to 18 hours ahead, in the form of a very simple polygon. These are accompanied by a volcanic ash advisory, which is simply a text description of these polygons. Since the eruption of Eyjafjallajökull in Iceland in 2010, the National Meteorological Services, who host the London and Toulouse VACs, have also provided supplementary concentration charts. And we have an example of one of ours from the right, on the right-hand side here. And these provide a more detailed description of where we think ash is in the atmosphere, and crucially, how much ash we think is there too. Over the last decade or so, there have been significant advances in our scientific and technical capability to provide a volcanic ash forecast. And QVA will reflect this. They will provide higher resolution information and more informative forecasts that are more useful and usable for the industry. We're providing quantitative output, which will mean that operators with approval or procedures in place will be able to use that information to generate more efficient routes. And we will also, as you've heard, be providing for the first time probabilistic forecasts, which will further help to optimize airspace planning. So what is QVA? Well, we're going to be providing 3 things. We're going to be providing ash concentration datasets, IWIXM objects, which are just simply more sophisticated polygons, and probabilistic datasets. That data will have a horizontal resolution of 0.5 degrees, and we'll be providing that data over 12 levels in the atmosphere with a depth of 50 flight level. And that'll be from mean sea level up to flight level 600. We will have higher temporal resolution data, so data will be output every 3 hours, and forecasts will go out to 24 hours. And we also have 5 new concentration thresholds, ranging from very low to very high. Practically speaking, if the slide will catch up. And that means that all of the VACs will now be forecasting how much ash is expected to be in the atmosphere. Forecasts will be at a higher resolution, and we will be providing more sophisticated polygons as well as concentration and probabilistic data. And this data, raw data, will be provided to aviation customers for the first time. There will be a phased transition across the VACs as we move towards QVA, and this is our suggested current timeline. From November 2025, the provision of QVA for significant volcanic ash clouds will be a recommended practice for those VACs able to do so. And from 2026, it will be a recommended practice, and it's expected to become a standard by 2030. At the London VAC, we hope to be able to make QVA data available to you from June of next year so that users can become familiar with it. But please rest assured, we will still be generating the volcanic ash advisory and graphics, your traditional products, during this transition. So we want to try and demonstrate to you now our QVA forecasts using a case study. So what you're about to see has been generated by the London VAC system. We have used a hypothetical eruption of a known active volcano in Iceland, which represents a moderate-sized eruption. And we've generated this output using real weather data. So although hypothetical, this does represent what could happen. Okay, so we're several hours into the eruption, and we have plenty of ash in the atmosphere. And on the left-hand side of your slide now, you can see the volcanic ash graphic that will be generated for this event. So this is generated from our modeling, from our forecasting system. And this is indicating the location of any ash above 0.2 milligrams per meter cubed. For the same scenario, we now have on the right-hand side our new QVA forecast. So this is for flight level 150 to 200, and we'll return to that in a minute. But what you can instantly see is that we have a more detailed description of where we think ash is in the atmosphere compared to the VAG. And we also now provide concentrations of ash in the atmosphere too. Now, you might remember that I explained that we're now going to be providing data over 12 different levels in the atmosphere. So I want to show you the advantages of being able to see where ash is in the atmosphere. So we're going to start now with flight level 0 to 50. So this is our very lowest layer. And we are going to then step through each new level in the atmosphere. The coloured box around your forecast allows you to compare the new forecast to what would have previously been described by the coloured polygon in the VAG. So this would have previously been described by the red polygon in your VAG on the left-hand side. So at flight level 0 to 50, we can see that ash is being transported towards the UK, but the high concentrations are constrained too close to Iceland. If we then move up to the next flight level, so flight level 50 to 100, we can see that the extent of the ash has increased. We have medium and high concentrations over the North Atlantic. Moving up again then to the next flight level, you can now see that ash is reaching Scotland, or the very top of Scotland. Moving up one more level, you can see also that the winds are shifting the plume round, and you can also see that ash is now reaching Norway. Up again now to the next flight level, and this would have previously now been described by your green polygon. You can see again that the location of the plume shifts with height, and that we have ash reaching the coast of Norway. Up once more, and again, the extent of the ash cloud continues to extend. So this is at flight level 250 to 300. But by flight level 300 to 350, the extent of the ash cloud begins to diminish. As we move to flight level 350 to 400, the ash cloud only extends as far as the top of Scotland. And by flight level 400 to 450, ash is once again constrained to just off the coast of Iceland. By the time we get to flight level 450 to 500, your ash cloud is much smaller, and it's mostly over Iceland. And by flight level 500 to 550, you can see that we're predicting that there's very little ash in the atmosphere. And this is because at this point, we're above the ash cloud. And finally, the very top level, we are predicting that there are no modelled ash concentrations greater than 0.2 milligrams per meter cubed at this altitude. So taken as a whole, you can see that by using the higher resolution vertical data, so you're moving from the lowest level in the atmosphere on your top left through the top row into the bottom row, and then you're at your highest flight level in your bottom right, you can see that you have a much clearer description of how both the location, extent, and concentration of the ash is varying with height through the atmosphere. As part of QVA, we're also going to be providing higher temporal resolution output. So data is going to be output every 3 hours. And this is important because depending on the wind fields, your ash cloud can be transported quite quickly. And so in the example we're showing here, we are showing how for this case study, the location and concentrations of your ash cloud are changing over a 6-hour period. So I've chosen 2 different vertical levels here. So for flight level 300 to 350, over this period of time, you can see how the extent of the ash cloud is changing and how it's looping back around itself. And then for flight level 350 to 400, you can see how at that level, the ash cloud continues to remain just reaching Norway. You can also see here that at the very tail of your plume, between flight level 300 to 350, we're predicting that concentrations of ash are less than 2 milligrams per meter cubed, which some operators may have a safety case in place to fly through. Okay, so that section summarizes the new concentration forecasts that we're going to be providing. We're going to move on now to look at the new IWIXM objects, which are the more sophisticated polygons. So these are showing you the maximum concentration across all vertical levels in the atmosphere. So they are helping to distill some of the information you've just seen. But they're much more sophisticated than the old volcanic ash graphic polygons. And that's because we are not limited by the number of vertices that we can use to draw the polygon, unlike the old product. You can also see that we are now able to visualize or show you the predicted concentrations within those polygons too. Lastly, moving on to probabilistic forecasts, which we're also going to be providing under QVA. So these are going to be new for all the VACs, but the idea here is to be able to provide you with a narrative on the confidence that we have in our forecast at a given moment in time. So the point here is that there are multiple sources of uncertainty associated with generating a volcanic ash cloud forecast. The most notable being the uncertainty associated with your eruption source parameters. As you can imagine, measuring the height of a volcanic ash cloud and definitely measuring how much ash is coming out of a volcano is really quite tricky. And there's also uncertainty associated with your meteorological data, which you will have all experienced in your day-to-day lives with the weather forecast. You will also know from your weather forecast that the level of uncertainty varies from day to day. Some days the weather forecast is spot on. Another day, you will have looked at the weather forecast, left home without an umbrella and been rather disappointed. So it's important to remember that, that there's a narrative there and that the confidence can vary from day to day. But there have been huge strides in the meteorological community in recent years to provide uncertainty associated with that weather forecast. And they call this ensemble meteorology. And we are now able to run our atmospheric dispersion model with this ensemble meteorology. So this means that we can represent the uncertainty in the weather forecast in our modeling. So the key meteorological parameters are the wind fields. We want to know which way the wind's blowing, at what speed, and precipitation, because this helps to remove ash from the atmosphere. And by representing uncertainty on these parameters and indeed all the other meteorological parameters too, we can represent the confidence in our forecast in both the expected location and concentration of ash in the atmosphere due to the weather forecast. So we have an example of one of our new probabilistic forecasts on the right-hand side of the slide here. These are being generated to show probabilities of exceeding each of the new concentration thresholds. So the example here is for probabilities of exceeding 0.2 milligrams per meter cubed. And in this case, a probability of 100% means that every weather scenario is predicting that you're going to get ash in that location exceeding concentrations of 0.2 milligrams per meter cubed. A probability of 50% means that half of your weather scenarios are predicting that ash is going to be at that location at concentrations of exceeding 0.2 milligrams per meter cubed. We're generating probabilistic forecasts for each of the concentration thresholds, and we're going to return to that in a moment. But returning first to our case study. So on the left-hand side, we have our volcanic ash graphic that was generated for this event. In the middle, we have our new concentration forecast for QVA for flight level 200 to 250. And on the right-hand side, we now have our accompanying probabilistic forecast for probabilities of exceeding 0.2 milligrams per meter cubed. And if you look carefully, you can see in the probabilistic forecast that our prediction of the extent of the ash cloud is slightly more spread. And that's just representing our confidence in the weather forecast that day. I mentioned that we're going to be generating probabilistic forecasts for each of the concentration thresholds. So here you can see for our case study, our forecasts for probabilities of exceeding 0.2, 2, 5, and 10 milligrams per meter cubed. And here you can see that we have higher confidence that the highest concentrations are constrained to the middle of the plume. So to summarize, the VACs are moving to new quantitative volcanic ash cloud forecasts. These changes represent improved scientific and technical capabilities in providing a volcanic ash cloud forecast, and will provide a more useful and usable products for the aviation industry. We're going to be generating concentration forecasts, IWIXM objects, which are the more sophisticated polygons, and probabilistic forecasts. And the new QVA forecast will give you higher resolution information on where ash is in the atmosphere, but also how much ash is there. For the first time, we're going to be providing the raw data to customers through an API, and Karen will be demonstrating this later this afternoon. But do rest assured that we're going to be continuing to provide the VAA and VAG alongside these QVA forecasts during the transition. And I will finish there and ask if there's any questions.